Hi, I'm going to present my project Shredder, which is on how to train noise distributions that protect privacy of systems deploying machine learning models. Machine learning is pervasive these days, from cars to handheld devices and smart homes. To get online services, we send our personal information to the cloud, where an inference task is executed on them and the result is returned to us. The information that we send is in raw format, which contains much more information than what is actually required for the inference task. Inference privacy is a very important issue. Conceptually, if we want to achieve higher privacy using noise, we would incur huge amounts of accuracy loss. Another method is homomorphic encryption, which achieves high privacy guarantees but is extremely compute intensive. We propose Shredder, which learns noise distributions that are tolerated by the neural network and do not harm accuracy while decreasing the amount of excessive information in the input. Our execution model consists of splitting the neural network into two parts and executing the first part on the edge device and the second, more compute-intensive part on the cloud. To increase the privacy of the edge device, we add our randomly generated calibrated noise, which obfuscates the excessive information while maintaining the accuracy. Shredder operates in two phases: offline noise learning phase, which happens once and is entirely executed on a server scale system, and test time inference, which is executed partly on the edge and partly on the cloud. For the noise training phase, we take a pre-trained deployed model and we freeze all of its parameters, which are shown by theta in the image. We then instantiate a noise tensor n with the same dimensions as the intermediate activation A, and we fill it with random Laplace noise. We then let the noise tensor train like it normally would using backpropagation and a gradient-based method with a loss function that we will shortly discuss. Once we have reached a desired accuracy, we take the noise tensor, fit it to a Laplace distribution, and save the parameters of this distribution alongside the order of the elements in the tensor. Our loss function has two main terms. The first one is the cross-entropy loss and is there to maintain the classification accuracy, and the second one is there to increase the amount of noise and decrease information to preserve the privacy. We try to do so by minimizing the signal-to-noise ratio, which we use as a proxy to the amount of information conveyed. Lambda here is a knob which helps us achieve a desirable trade-off between the accuracy and privacy. To recap the noise distribution training phase, we first initialize a noise tensor with Laplace distribution. We then train this noise tensor to regain the accuracy and reach a desirable state. We then fit this trained noise tensor to a Laplace distribution and save the parameters of this distribution alongside the order of elements of the noise tensor. We repeat this until we have collected multiple noise distributions. For the noise sampling phase, we first randomly choose a distribution and saved order tuple from our collection of distributions. We then draw samples from the saved distribution to populate a noise tensor and rearrange the elements of this noise tensor to match our saved order. We apply this noise tensor by adding it to the activation, and we then send the noisy activation to the cloud for further processing. In order to show the amount of privacy, we use mutual information between the transferred noisy intermediate activation and the input image. We compare this mutual information to the mutual information between the original intermediate activation and the image. We found that across benchmarks, we lose 74% mutual information in average, while losing less than 2% accuracy. As a more intuitive demonstration, we show that if we define a primary task, such as gender classification, and a private task, like identity classification, Shredder can cause misclassification on the private task with minimal harm to the primary task's accuracy. We tested two variations of Shredder here. One, the conventional Shredder, which we assume has no access to the private labels and is thus unaware of what it is supposed to protect against, and also a variant of Shredder that has access to the private labels. In the image, we have compared our method to deep private feature extraction, which is an intrusive privacy-preserving mechanism that requires access to the private labels. For higher accuracy levels of the primary task, Shredder outperforms DPFE in terms of misclassification rate, as shown in the image. I am currently looking into expanding Shredder in different directions, like using the noise to add uncertainty to neural networks, making models more robust to adversarial examples, and also providing differential privacy guarantees. Thanks for listening to my talk.